to our next speaker, who is Casey Lamb. Casey, there we are. Excellent. Hello there. And Casey will be telling us about hunting for isolated black holes with microlensing, so at the opposite end of the mass scale. Casey, you can share your screen whenever you're ready.
Okay, thanks. Okay, is that working?
Yeah, that was great.
Okay, great. Then thanks, Rachel. So yeah, today I'll be talking about finding isolated black holes with gravitational microlensing. And some of the results I'll talk about, we just submitted to AppJ for review, and the preliminary results are at this archive link. Okay, so the motivational question that we're ultimately trying to answer is how many black holes are there in the Milky Way? And black holes are an end product of stellar evolution formed when massive stars die. And there should be 100 million of them in the Milky Way. And of those 100 million, we actually only have mass measurements for about 24 of them. Most of them are in X-ray accreting binaries. And more recently, some have been detected in these wide non-interacting binaries. But binaries are not a representative sample of the black holes in the Milky Way. There should be other types of black hole systems. And in particular, a large fraction of them should actually be isolated single black holes. And only with a full understanding of this complete black hole population can we actually answer this question of how many black holes are there in the Milky Way, as well as questions like what is the black hole mass distribution, what are the formation channels, when they're born, do they get kicks, and how big are they? And how does the Milky Way black hole population compare to extragalactic samples from LIGO? And so isolated black holes are important in completing this picture. And so we need to detect them. But they differ from the other types of systems shown in this picture because they're not in binaries. And if you don't have a binary companion to interact with, it makes them difficult to find because by definition, they're dark objects. And so a lot of the really great talks earlier today and yesterday talked about why microlensing is great for finding isolated dark objects. And so all I just want to say here is that the combination of photometry and astrometry is key to measuring these masses of isolated dark objects. So kind of moving on to what we've done so far, this is example kind of proof of concept that can be applied to Roman. So we've analyzed a sample of 5 black hole candidates. So these candidates were selected about 10 years ago from photometric microlensing alerts from ground-based microlensing surveys such as OGLE and MOA. And then they were followed up astrometrically for the next 8 years afterwards with the Hubble Space Telescope using the WIFC-3 UVIS instrument. And this program was initiated by Kailash Sahu. And so what I'm showing here are the ground-based light curves of these 5 different candidates. These are their names. And you can see that the ground-based light curves, they're very, very densely sampled. So these ground-based microlensing surveys often sample about 10 times a night. And so we have very good light curve coverage. On the other hand, HST astrometry data is very hard to come by. And so over this 4 to 6 year period over which these candidate black holes were observed to get their astrometry with HST, there's about 8 observations total per target. And so, but the important thing is it's the combination of the photometry and the astrometry that will let you measure lens masses. So that's what we did. We jointly modeled the photometry and astrometry for these 5 black hole candidates and derived what their masses were. So that's what's shown here on this figure. And so just to point out some of the relevant quantities. So this is the mass of the lens of the these different targets and the probability. So you might notice that there's 6 different contours when I said earlier there are only 5 targets, and that's because this particular target, OB110462, depending on how you model it, you get 2 different lens masses. And so just kind of to explain a little bit more about why that is, the DW and EW that we've appended to the names, those are describing the two different ways we have to approach modeling this event. And as I mentioned earlier, there's way more ground-based photometry than there is space-based high-resolution data from HST. And so in the modeling, depending on how you want to weigh those two different data sets, you can get a slightly different result. Because although you need both data sets to measure the mass of the lens, in some cases there are common parameters where each data set provides an independent estimate of that parameter. So the DW estimate, that stands for default weighting. In that case, each data point from all these different data sets weighs equally into the likelihood. So in this case, the ground-based photometry has the most weight. On the other hand, EW, that stands for equal weighting. Each data set contributes equally to the likelihood. So the ground-based photometry is considered one data set, and then the high-resolution data from Hubble, that's considered another data set. But the thing to note is that for this target, in particular OB110462, either way, the mass of the lens in that case falls in the kind of mass gap for black holes, neutron star black hole mass gap between 2 to 5 solar masses. And so that's interesting. We just now have to rule out that, it's not a 2 to 5 solar mass star. If the 2 to 5 solar mass object is dark, then that is a good chance that means it's a neutron star or a black hole. And so we can do that by combining these mass measurements we have along with the photometry that we have, the images. And so by looking at the images, we can figure out what is the brightest star we can hide in this image. If the brightest star we can hide the image is brighter than what is actually allowed that we see when we take the picture, that means we have a dark lens. And so that's how we calculate these lens type probabilities of whether we have a star or a compact object, what type of compact object, brown dwarf, white dwarf, neutron star, or black hole. And for these 5 candidates, most of them are either white dwarfs or stars, well, maybe neutron star, but OB110462 is a really good highest chance to be a black hole or a neutron star. And so this is really cool, and we can put the sample of 5 candidates towards answering that question that I posed earlier about how many black holes are there in the Milky Way. So that's what's shown here. This is the probability of getting n black holes in our samples. So we have 5 candidates. That means we can either make 0 to 5 black hole detections, and the probability of that number of detections. So in this case, depending on how you choose to interpret this OB110462 event, you get slightly different probabilities for the number of black holes that you get in the sample. But either way, it's most likely, based on these observations, that we either have 0 or 1 black holes. And that's confirmed by analyzing the sample as a whole. And the underlying galactic model we use to evaluate these probabilities assumes this 100 million black hole number. And the way we combine the results from the previous slide to here is that in this model, longer events are more likely to have black hole lenses. And so the reason that it's more likely that we have fewer black hole detections and more black hole detections is that the different events in the sample had a relatively low probability of being black hole lenses just based on their time scale. And so based on this small 5 sample detection, we're currently still consistent with 100 million black holes in the Milky Way. So now I want to kind of turn to what Roman can do about this question. And Roman is awesome because it has simultaneous precision, photometry, and astrometry. With its big field of view, wavelength in the IR, and staring at the bulge, it's going to have lots of stars detected, and which is going to lead to awesome astrometric precision. As talked about earlier, if you can combine all these measurements together with the incredible time sampling, you can get a really good astrometric precision, better than, about 4 times better than we can currently achieve with state-of-the-art like Keck or HST. So this is a kind of quick illustration that I made just to show. This is the gray line is the astrometric microlensing signal you'd expect for a 3 solar mass star. With the blue data points, those are simulated HST observations, so similar to what we have from that data set I showed earlier. It's very sparse, but for Roman, with its multiple seasons, it's very dense time sampling, and again, the great astrometric precision, it's so dense that it just looks like a blob here. You get really great coverage, and that's really important to constrain the astrometric signal. So it's awesome there. And it also helps in this other way, the fact that it's simultaneous photometry and astrometry. You don't have to do this individual follow-up like we currently do with looking on the ground-based alerts and then selecting only a handful that we can follow up. This can help avoid potential selection biases and also just lets us have the entire sample at once. It's not like now we're limited to 5 objects per 10 years or something like that. And so the other thing is that this means Roman can measure the Milky Way black hole function. So here's a simulation of the black hole distribution we assume in our galactic model of the Milky Way. Incorporates a star formation history, an initial final mass relation that maps initial stellar masses to their final remnant masses, and then the initial mass function. And that gives you this kind of fiducial black hole mass model, mass function model. Then if you simulate then time into the simulation, figure out what lens is what, you can figure out what the observed microlensing event should be. And then by applying observational constraints, what should Roman be able to detect? And for these events that Roman should be able to detect with photometric and astrometric microlensing, which of those are black holes and what are their masses? So that's what's shown here on the right. And that, as talked about earlier, Roman should be able to measure hundreds of black hole masses. And so if you measure this, you can go back to the underlying distribution with an efficiency correction and understanding the selection that you have from imposed by microlensing. And so you should be excited because not only are you going to find lots of planets, but you're also going to find lots of black holes with Roman. And so these are kind of just the points I hope you take away, and thanks for your attention and happy to take any questions.
Thank you very much, Casey. That was a fascinating talk. And I'm sure it's going to stimulate plenty of debate. So starting off, Valerio already in the chat screen, is there any statistical justification for the EW approach in the OB 110462? It might be dangerous to give more weight to sparse data sets.
Yeah, it's a great point. So the point basically is that the 2 data sets, the photometry and the astrometry, are basically in tension right now in the inferred relative proper motion of the source and the lens, depending on whether you believe the photometry or the astrometry. And so I think the kind of most important thing right now is to understand where that discrepancy is occurring. The different weighting schemes are kind of more kind of exploratory and trying to understand what the implications are of choosing either data set over another. But ultimately, I think the way to go is understanding maybe whether or not it's a systematic somewhere in the photometry or the astrometry or both, or whether or not, both data sets are actually robust. And it's just that the model, we need a more complicated model, like instead of just having a single lens and a single source, we need a binary source model, for example, or something like that.
Thank you. And I see another question from Samson Johnson in the Slack channel. He says, great talk. Do you have any slides with different IFMRs? And how well will Roman differentiate between those? I might have missed it on one of your slides. Sorry if so.
Yeah, well, so I don't actually have any other different initial final mass relations here, but we have, we're working with a really talented undergrad at Berkeley. Her name is Sam Rose. And so she's been working on implementing different initial final mass relations into our simulated galactic model. And so she submitted a paper a few months ago. It's currently under a referee report. And so hopefully that should come out soon. And that has kind of the implications of whether or not these different initial final mass relations, depending on what kind of you assume about supernova physics, and and things like that, whether or not that can be detectable with surveys like Roman or Google.
Thank you. And if I could just pick up on one point you ended with, perhaps I misunderstood something, but when you made the prediction for the number of black holes that Roman would be able to detect, were you considering just the exoplanet survey and the bulge, or all of the Roman data set in the both surveys?
Yeah, so that is just assuming from the bulge time domain survey.
Right. Have you considered the wide area survey as well?
Yeah,
or is
no,
that too partially sampled?
yeah, we haven't considered that yet.
Okay.
Because we haven't simulated the those other different fields yet. But that'd be really interesting because people have been finding microlensing events away from the bulge. I think it's just that the event rate is so small that there might not be that many events, because black holes are only about 1% of the microlensing events. So
it does drop, yes, but the deeper that you go, and of course Roman will go very deep, then it somewhat compensates for that. So it might be worth something considering. But this is a super exciting result. So thank you very much for that talk.